Now that we have equations to work with when we're talking about lines in space, let's look at how we might work with these ideas that apply to some real life situations. The first application of these techniques will be finding the distance from a point to a line. These are important considerations if you're designing video games, trying to figure out positions with respect to orbits and that kind of thing. So if I want to find the distance from a point to a line, we can use the vector equation of the line that lies in the direction of a vector v, and the relationship between the cross product of the vector v and the vector from some initial starting point of vector v to another point q that lies in space. So let's look at how we will do this. We have looked at cross products and we found that the magnitude of the cross product of two vectors v and pq is equal to the magnitude of the vector v times the magnitude of the vector pq times the sine of theta. Notice that when I construct my two vectors pq and v, and then I draw a dotted line from a point q at the end of pq to the line in the direction of the vector v that intersects at q prime, that distance given through trig is equal to the magnitude of PQ times the sine of theta, which is the angle between PQ and V. So that my magnitude of my cross product is equal to magnitude of V times the product of the magnitude of PQ and sine theta, but the magnitude of PQ and sine theta is D. So we plug in D, then we divide through by the magnitude of V, and I find that the distance between a point in space and a line that is in the direction of a vector v can be expressed as the magnitude of the cross product of v and pq divided by the magnitude of v. So let's work an example. Let's find the distance between the point Q with coordinates 5, 6, 1 and the line given by x is equal to 1 plus 3t, y is equal to 3 minus 4t, and z is equal to t plus 1. The parametric equations that I'm given for my line can be decomposed in order to give me my two vectors. My v vector is the coefficients of the terms involving t in my parametric equations. So my v vector is given with components 3, -4, and 1. My point p is the constants in those parametric equations, so that my pq vector will be the difference between the coordinates of my q point and the constants in my x, y, and z equations. In other words, my vector pq is equal to a vector with components 5 minus 1, 6 minus 3, 1 minus 1, which gives me a vector with components 4, 3, and 0. Now I know my vectors v and pq, I can compute the cross product. V cross pq is the determinant of a 3 by 3 matrix, and I can perform that cross product operation either using minors and cofactors or the method of diagonals, and I will get a vector that is expressed as -3 in the I hat direction, plus 4 in the j hat direction, plus 25 in the k hat direction. The magnitude of this vector is equal to 5 times the square root of 26 once I simplify it. The magnitude of my vector v is the square root of 26, so my distance between the point Q and the line given by the parametric equations becomes 5 square root of 26 over square root of 26, or it simplifies to 5. So now you get to try it. Pause the video and find the distance from the point Q with coordinates 1, 3, 5 to the line given by the parametric equations x is equal to -2 plus t, y is equal to 4 minus 2t, and z is equal to 1 plus t. When you're ready, restart the video to check your understanding. The first thing I want to do is identify my v vector, which is, as you recall, the coefficients of the t terms in my parametric equations. So my v vector is equal to the vector with components 1, -2, and 1. My PQ vector is given by subtracting the constant terms in my x, y, and z parametric equations from the coordinates of x, y, and z in my point Q. So my PQ vector is given by the vector with components 1 plus 2, 3 minus 4, and 5 minus 1. This gives me a vector with components 3, -1, and 4. Now I can compute the cross product V cross PQ using the determinant of a 3 by 3 matrix, as we've always done. I get a vector that's written as -7 I hat minus j hat plus 5 k hat. The magnitude of that cross product is simplified to 5 times the square root of 3, and the magnitude of my v vector is the square root of 6, so that my distance between that point and that line that I was given is given by 5 square root of 3 over square root of 6, or I can also write it by rationalizing the denominator as 5 square root of 2 over 2. Another handy application of using these equations of lines in space is to find intersection points between those two lines. So we can use this to determine not only if there's an intersection point, but we can also use them to determine if my lines are parallel or skew, which is to say they neither intersect nor are they parallel. Recall that if two lines are parallel, they will have no points in common unless the two lines lie on top of each other and are identical. Intersecting lines will have a single point in common, and skew lines will give me an inconsistent result when I solve the system of equations that involve the parametric equations for the two lines. So let's work an example. I want to determine if the two lines are parallel, if they intersect at a single point, or are skew. And my two lines, L sub 1 is given by x is equal to 2t, y is equal to t plus 2, z is equal to 3t minus 1. And my second line, L sub 2, is given by x is equal to 5s minus 2, y is equal to s plus 4, and z is equal to 5s plus 1. V sub 1 vector is given by the coefficients of t in my L sub 1 parametric equations. It is a vector with components 2, 1, and 3. V sub 2, likewise, is a vector with components that correspond to the coefficients of s in my L sub 2 line. That's a vector with components 5, 1, and 5. Because these two vectors are not scalar multiples of each other, the lines are not parallel. The next thing I do is construct a system of three equations that set the x, y, and z equations in my parametric definitions of my two lines equal to each other. So the first equation is 2t is equal to 5s minus 2. My second equation is t plus 2 set equal to s plus 4. And my third equation is 3t minus 1 is equal to 5s plus 1. Now I use my techniques for working with systems of equations. So I take -2 times equation 2 and add that to equation 1. This gives me the equation 1, 2t set equal to 5s minus 2, and I'm going to add -2t minus 4 is equal to -2s minus 8 to it. When I do that, I get negative 4 is equal to 3s minus 10, and I solve that for s and get s is equal to 2. The next step is to plug 2 in for s in equation 1 and solve for t. I get 2t is equal to 5 times 2 minus 2, and that gives me t is equal to 4. My final step is to plug 2 and 4 into equation 3. I get 3 times 4 minus 1 is equal to 5 times 2 plus 1. This gives me 11 on the left is equal to 11 on the right. This is a true statement, and it tells me that my lines intersect at a single unique point. So now you get to try it. Pause the video and determine if the given two lines are parallel, intersect at a single point, or are skew. When you're ready, restart the video to check your work. The two lines are given by L sub 1 is defined by the parametric equations x equal 4 plus 5t, y is equal to negative 2t, z is equal to 1 plus 3t. And my second line, L sub 2, is given by x is equal to 10s, y is equal to 6 plus 4s, and z is equal to 4 plus 6s. The first step is to figure out what my v sub 1 is. That is a vector with components 5, negative 2, and 3, which I read right off of the coefficients of t in my equations for L sub 1. V sub 2 is equal to a vector with components 10, 4, and 6. These again are the coefficients for my s in L sub 2. Be careful with your signs here. It's tempting to look at this and think that these are parallel, but because the signs are not consistent, we have neither vector being a scalar multiple of the other, so they are not parallel. Next, I need to set up a system of equations. My system of equations, equation 1 is 4 plus 5t is equal to 10s. Equation 2 is 2t is equal to 6 plus 4s. And equation 3 is 1 plus 3t is equal to 4 plus 6s. Now I'm going to take negative 3 times equation 2 and add that to 2 times equation 3. So my negative 3 times equation 2 gives me negative 6t is equal to negative 18 minus 12s. And I add that to 2 times equation 3, which is 2 plus 6t is equal to 8 plus 12s. And I end up with 2 is equal to negative 10. This is inconsistent, so that my lines are skew. This is how we can take the idea of equations in space and use them to solve situations involving lines. Let me know if you still have questions.